Okay, so 2022 applied maths paper, connected particles question 4 questions. So let's have a look at this. Slightly unusual one this year, I would have thought. Slightly more complicated than normal. So let's have a look at it. Question 4A. So block C, it's on a rough table. So they're being a little bit evil, putting a bit of friction in. So D and F, no, D and E. Okay, block C, mass 6m, rough table. So we presume it's going to go down that way. So the friction force is going to be that direction. So mu r. Put the reaction there. It's connected by lead in a strict string. The usual blah blah blah. Block D mass 3m. D is connected by another light and extensible string, so mass 2m. Coefficient is a third, is it? And it's released from rest. So mu is a third there. And it's released from rest. Separate diagrams. Okay, so the easiest one to put in, the force is the mass. So that's 6 mg there. It's got a reaction going up, or it'll have a tension. Tension always pulls it away from the object. And the friction force is going to resist the motion, which we're going to assume is in that direction. Let's say the acceleration is A. This guy, tension is going to pull away from it. Yeah, now the important thing about, okay, so, and that one is going to have 3 mg. Now these should be on separate diagrams, but that one is going to have a different tension, so we're going to have to call that T1, or let's call it T2 actually. And that one will have T2 going up there, and its weight is 2 mg. So just important to remember that there is different tension on that string because they're totally different strings. Actually, it might be just easier to call that T1 and that T1. Okay, find the acceleration of C. Well, the acceleration is going to be the same for them all because they're all connected by taut strings. The string stays taut all the time, does it? Coefficient, yeah, system release from rest. Tension in each string. Well, yeah, they are going to stay, they're going to be the same, are they? Let's see. Yeah, okay, so that moves down. That will have to move down at the same speed. The strings are taut, or will it? It will, yeah. Okay, so we're going to have the same acceleration, A. Okay, so force is acting on each block. Okay, so let's have a look at C. Well, in that direction, so we're going to have T1 minus a third, so mu r, so a third of 6 mg, and that's it, is equal to 6 ma, yeah? D is going to move down, so we're going to have 3 mg. Now, it will have that tension as well, so plus T2, pulling it down, minus the tension pulling it up, is equal to 3 ma. And E is going to be moving down, so it'll be 2 mg minus T2, which is pulling it up, is going to be equal to 2ma. Grand. So find the acceleration of c. We'll find a. So let's see what cancellation we can do. So let's see. Well, if we take d minus e here, put it down here, d minus e, then hopefully they will cancel. So that will be 1mg. They will cancel. So minus t1 is equal to ma. So we get t1 is equal to m into g minus a. Substitute that into the c equation. G mg minus ma minus 2mg is equal to 6ma. So we get 7ma is equal to minus mg. So a, getting rid of that, is equal to minus g over 7, which would indicate that a is going to go the other direction. Fine. Is that possible? Doesn't seem to be possible, but look, let's see how we are at the moment. Okay, something is up, but let's see if it makes sense. Okay, so right, how do we do this? So t1. Okay, let's just make sure we get that right. So t1. Okay, so yeah. So okay, so adding those. There's the problem. Should be adding those. So that's 5mg. Okay, so that's where the problem is. So let's add them. 5mg. They cancel. Minus t1 is equal to 5ma. So t1 is equal to 5m into g minus a. Now let's bang that into c. So 5mg minus 5ma minus 2mg is equal to 6ma. Okay, this is probably more like it. So it's 11ma is equal to 3mg. Looks a bit more like it this time. So a is equal to 3 over 11g. So the acceleration is equal to the unbalanced force over the total mass. Will that be okay? Unbalanced force over the total mass. Okay, so that's the acceleration. It's moving in the positive direction, so that looks a bit more reasonable. Okay, tension in each string. Okay, so simple substitution then. So T1 is equal to 5m into g minus a. So that's 11g over 11 minus 3g over 11. So tension is equal to 5m by 8g over 11. So tension is equal to 40 mg over 11 for T1. And it's positive, so that seems okay. T2 then, how are we going to get that guy? Well, T2, we'll get it from E. Seems to be the most reasonable way to get it. Okay, so E says that 2mg minus T2 is equal to 2ma. So T2 is equal to 2mg minus 2ma. So it's equal to 2m into g minus that guy. So T2 is going to be equal to, well, 8, but 16 mg over 11. So T2 is a lot lower than T1. So T2 is going to be less than T1. Does that make sense? Yeah, it does. So T1 is going to do the heavy work shifting this guy, and T2 is going to do a bit less. So that's okay. Right, so tension and strength, that's it. Okay. Not the easiest one, I would say. Usually you get an easier one, part A there. Okay, particles A and B. So part B, let's have a look at that guy. Right. Not an equilateral triangle, isosceles. 30-30. So let's just fill in the other guy. That means the other guy is 120. Got a pulley there. And this. Okay. So particles A and B. Mass is M, so it's a bit unbalanced. M and 2M. Okay, so more weight than that side. Okay, but light and access with below the poly. One particle resting on each of the faces which are smooth. Thank God for that. So we don't have to worry about friction. Each of the inclined face of the wedge makes angle 30. Wedge of mass 3m. Rests on a smooth horizontal table. Thank God for that. Release from rest, find the acceleration of the wedge. Okay. So let's put in, they don't give the normal nice easy build up, draw the forces acting on each one, but let's just draw some of them in anyway. So that's 3mg there, everything is smooth, so we're okay. Okay, so now, yeah, so this guy is mg acting downwards, that guy is 2mg acting down there. So this guy, okay, we're going to need the 30 triangle. That's going to be popular, so let's do that in. What is that? That's 1 root 3, 2, yeah? Okay, so sine 30 is a half, cos 30 is root 3 over 2. Okay, so going down that way is cos 30, so root 3 over 2 mg, 3 over 2 mg, and going across that way is mg over 2. Okay, bit crushed in, but it'll do for the moment. This one is 3, so that's cos 30, so root 3 over 2 in there. Root 3 over 2, 2 mg, so it'll be mg root 3 going down that way. And that way will be mg. Okay. We're going to have to decide which way they're going to go. So presumably we're going to acceleration of this particle system, we're going to say A that way. So that one's going to go up there. Because that's the heavier one, we're going to just assume it's going to go out there. So it's going to go down that way, which will tend to push the wedge that way. So let's say F is that way for the wedge. Okay, so that would be that way for the particle, and that way for F, with 30 degrees between them. So that's going to be equal to A cos 30, and that up there is going to be A sine 30. And similarly for this lad. So, system release for Wedge, find the acceleration of the wedge, so we need F. Well, okay, so we're going to have a few reactions as well. So, okay, so this particle here, let's have a look at it. Or do we need, let's, okay, so these guys, we're going to have a reaction like that in R1. And we're going to have a reaction like that, R2. Okay, so where that is going to be 30. Okay, so let's have a look at particle system. Oh yeah, of course there's going to be tensions as well in those strings. There's going to be the whole lot. There's going to be everything. We're going to have a lot here. Okay, so lots of reactions, lots of tensions. Okay, the reaction is going to be perpendicular in. So for the wedge, we need to see which way it's going to go. Yeah, so that reaction is going to be like that, and it's going to be sine 30. It's going to be R1 sine 30, which is a half. So R1 over 2 going that way. This guy is going to be, so in the horizontal direction, it's going to be R2. God, but I get the orientation right. Jesus. Where's my horizontal? Okay, so that reaction we need to resolve it in terms of what's going down and what's going across. So that is your 30. So that's your sine 30. So that's R2 over 2. Yeah. So R2 over 2 is going that way, and downwards is going, yeah, okay. So downwards is going root 3 over 2 R2, and this side root 3 over 2 R1. Okay. So quite a complicated wedge there. S and 3mg, yeah? Everything is smooth, so we don't need to worry about that. Okay, so I don't think the up-down is going to be a problem. They're all going to be equal, so your downward forces, so root 3 over 2 R1 plus root 3 over 2 R2, and your other downward force is 3mg, the weight, and that's all going to be equal to that, S, the reaction with the table. May not need that, but it's handy to have it. Okay, now, we said it's going to go that way, so F. Okay, it's going to go in that direction. So the reactions, so let's have a look. So that way, so it's going to be R2 over 2 minus R1 over 2. And what else? Is there anything else? Don't think so. That's going to be 3mf. Okay, so let's simplify that a little bit. So we'll get 6mf is now going to be equal to R2 minus R1. Okay. So we need F, so we're going to have to just have a look at those guys. So now let's have a look at the particles. Jeez, this is getting involved. Fucking hell. That's tension there, that's tension there. Same tension. Okay, so this guy, tension pulling it that way. What else? The weight it's, which direction did we say it's going to go? We're going to go up that way with acceleration A. Now we'll have to resolve it in terms of its absolute. That's just relative to the wedge. Okay, the mg was down that way. Yeah. And that was just 1 mg, yeah. So it's mg, so it's mg over 2 is going to be that way. And then in was mg root 3 over 2. Similarly for that guy, tension's going to pull that back. It's going in that direction. It's going to be, it's mg this way. And down was mg root 2, yeah? Is that right? Root 3. Okay. And that is it. Okay, so that direction. Now, the acceleration. Okay, so up that way. The acceleration is there, but the wedge is going that way. So, yeah, so that is that is that way, so the acceleration of A is up the wedge and across the way. Yeah, that should be alright, that's fine. Okay, so that is, okay, so we need to get a perpendicular one. Okay, so that's A and that's F. So yeah, sorry, we need to resolve that. So that's F sine 30, which is half. So that's minus F over 2. Okay, and that one going down is root 3 F over 2. Okay, so yeah, so that way T minus mg over 2 is equal to mass by the acceleration relative to the wedge, factoring in this guy, equals that. Okay, now in there you have mg root 3 over 2 is equal to m into root 3 f over 2. Okay, this guy is going to be similar, except in this case it's going that way, so it'll be mg minus t is equal to m a, the f is going that way, so it's a to f over 2, same thing, yeah, because it's cos, and cos is, okay, so it's minus f over 2, so it'll be cos 30, which is root 3. I think these, that's a, so that portion of f going backwards there is cos 30, so that should be the root 3 over 2 bit. So that's the root 3 over 2. And this going inwards is f over 2. Okay, similarly here, a minus root 3 f over 2. Is that correct in terms of the relative velocity of the wedge? The wedge is going that way. So, yes, it will be cos. Yeah, okay. And then this guy is mg root 3, because everything is kind of doubled here because of the two masses. Oh yeah, that should be 2m. 2m into f over 2, isn't it? Sine, yeah, f over 2. Okay. Quite involved. Quite involved. Okay. Is that going to be consistent? I hope it will. Okay, so that would say that mg, oh yeah, okay, we want f there. So f, we can do a bit of cancellation. F is equal to g root 3. Yeah. F is equal to g root 3. Will that come out of this one as well? Let's just check. F, well, cancelling that and that. F equals g root 3, yes. Okay, so that actually gives us the acceleration of the wedge. Okay, so that's, okay, I thought we'd have to do a bit more on that. But that gives us the acceleration of the wedge. Alright. Grand, so that's F. And that gives us such. Okay, that's grand. Quite a lot of calculation there though. That was quite tricky, I would have thought. F equals g root 3. So let's just sanity check that. So in other words, F is going to be bigger than g. It's going to accelerate bigger than g. Yeah, that's probably fine, I suppose. Yeah. Yeah, a lot of simultaneous equations, and just trying to keep an eye on that triangle as well for sine and cos. So there we go. That's the connected particles. I would say that was quite a tricky connected particles question.